When I first began discussing Isaac Newton's contribution to our science, I mentioned that he created for us three laws. And if you're paying careful attention, you probably realize that so far I've only talked about two of those three laws. The first law is the law of inertia, the natural tendency of objects to persevere in their motion. And when they don't do that, that's how I define forces. Forces are natural constraints or conditions in the universe that cause objects to behave other than an inertial way. The thing about the first law is that it doesn't really solve any problems. It doesn't get you any answers. But if you're going to use Newton's laws to solve problems, to get the answers that you want, to describe a physical phenomenon or perform a laboratory experiment, you need to keep it in mind. You have to understand that all objects have this natural tendency. You need to internalize that idea so you can use it in your physical reasoning. But it doesn't solve any problems. It doesn't get you any numbers. It's Newton's second law that gets you the answers that you're looking for. Newton's second law is the one, sigma F equals ma, that allows you to calculate things. The third law of Newton, which is my topic for today, is similar to the first in the sense that it doesn't get you the answers to any questions. That is, you can't calculate numbers with it. It's just a bit of reasoning that you have to keep in mind when you describe the natural behavior of physical systems. The third law. It's not as elegant as the first law when stated out. In fact, it's a little bit awkward. So it'll require a little bit of analysis to work out what this language actually means. When one object exerts a force on another. So far, I've been talking about the behavior of individual objects, single objects. But the fact of the matter is, the nature of our universe is interaction. All of the interesting things of nature happen when one system or object interacts with another. So I begin with one object exerting a force on the other then reacts with an equal and opposite force. It's a very simple statement, but it has some subtlety to it, and sometimes when it manifests in our everyday lives, it's a little difficult to appreciate that this is actually what's happening and to accept the interpretation. The shorthand for this is often called the law of action-reaction. When one object exerts a force on another, the other reacts with an equal and opposite force. The details. Forces of interaction are always between one thing and another. Most often, in our everyday experience, it involves physical contact, but it's not necessarily true. The moon goes around the Earth under the influence of the Earth's gravitational force, but there's no physical contact. So it really happens anytime there's an interaction, whether it be direct physical contact or action at a distance, like gravity or electricity. And you have to have a pair of forces in the third law, one object acting on the other. Now, these two forces are equal in magnitude and opposite in direction. So that might put an idea in your head that they add to zero. Action-reaction forces don't add up to zero because each one of those forces acts on a different object. Each object in the interaction is going to react to the force impressed upon it, not to both forces simultaneously. It's not often stated, but it's a really important point that when there are two forces that are action-reaction, the forces always have the same nature. What I mean is that they're forces that we would give the same name. For example, here is a car, and I'll imagine that the car is accelerating to the right. What makes the car accelerate? Well, you might say the engine, and you'd be right, because of course without an engine in the car will not accelerate to the right as shown in the diagram. But really what happens is that the engine regulates a combustion process that causes rotation to a transmission along a shaft that then goes to a differential, which then turns the wheel, and the wheel is in contact with the road. What makes the car go forward, accelerate forward, is the force of friction between the car and the road. And you know this because on the car we put nice rubber tires with good traction. If you don't have good traction, then you're going to slip and the car will not proceed forward the way that it's supposed to. Also, we drive on days when the weather conditions assure us that there'll be plenty of friction between the car and the road, because it is the friction force that causes the acceleration. You know, it's even true as I walk around the room. My ability to accelerate myself forward and change my motion, as I talk about Newton's laws, is I use my foot to push backward on the floor. Now, pushing backward on the floor is an influence exerted on the floor, but because of Newton's third law, I realize that the friction force that I exert backward on the floor is exerted forward on me. And so I propel myself forward with a friction force that is an action-reaction pair with the friction force that I push backwards. And the same thing's going with the car. The car pushes backward on the earth, and then the car moves forward. Both of these forces are friction forces. That's what I mean by forces of the same nature. Action-reaction pairs of forces are always of the same kind of force. Now, here is a common mistake that is sometimes made in this particular area of our physics. As I stand here in front of you, I have weight, and my weight could be drawn on a diagram straight downward toward the center of the earth. The floor pushes upward on me with a force of contact, much like when Slim was standing on the elevator. He had weight downward and a contact force upward. The weight and the contact force are not an action-reaction pair. As I stand here, the force of gravity downward on me and the force of the floor upward on me are equal in magnitude and opposite in direction. It's true, but they're not the same nature. One is the force of gravity and the other is a normal force of contact. They don't have the same nature. They're not an action-reaction pair, but there is a pair, but the pair is really hard to spot. I have weight. Weight is the gravitational force pulling downward on me due to the earth. The reaction force is me pulling upward on the earth with a force of gravity. Now, I know at first that sounds a little bit absurd. When I go hopping around on the surface of the earth, I do all the moving, and the earth does not. This is only because when the gravitational force that acts on me, which is my weight, is revisited again on the earth is so massive that the earth doesn't accelerate. So when I go to a high place and jump off, me and the earth are exerting equal and opposite forces on each other, but I do all of the accelerating because my mass is so small. It's difficult to get your head around that because the earth is so incredibly huge and you are so very, very tiny in comparison. So let's bring it a little bit back to scale. Here I have a cannon and a cannonball. Their masses are way different, but it's not as bad as the earth and a person. So this I can use a little bit of imagination. Before I do any kind of calculation, imagine this. A cannonball, which is quite heavy, is put into a cannon, which is preposterously massive. And then you fire. Off it goes. We know that the cannonball gets shot way across the battlefield. That's the whole point. But you also know, if you think about it, even though you're not a person who's ever fired a cannon before, you also know that the cannon goes backward in the opposite direction. The common term for that in everyday language is recoil. The cannonball goes to the right and the cannon goes to the left. And the reason why is that the cannonball and the cannon exert action-reaction forces on each other according to Newton's third law. I have imagined what a cannon force would be. It's got to be a lot of newtons. So I've asked you here to suppose that the force that the cannon exerts on the cannonball is 10,000 newtons. A lot of force. What kind of force is that? Well, a cannon has gunpowder in it. The gunpowder is ignited, and then those gases expand. So it's actually the force of explosive gas pressure, which was never on my list of forces that I'd expect in problem solving, but I know that the explosion inside of a cannon exerts a force. The cannonball then experiences a 10,000 Newton force, but the cannonball exerts a force back on the cannon that is equal in magnitude. You see here I've suggested 10,000 newtons, but opposite in direction. They're an action-reaction pair. What is the nature of the force that the cannonball exerts on the cannon? Gas pressure force. the same force. It has the same nature. Now, the cannon and the cannonball have the same force acting on them. But it's critically important that we appreciate that that doesn't mean that we're going to observe the same motion. And here's why. Newton's second law tells me that the sum of all forces is equal to the mass times the acceleration. Here, I've rearranged it so that the acceleration is the net force divided by the mass. In the case of the cannon, the acceleration of the cannon off to the left, what we would call recoil, can be calculated as the force, 10,000 newtons, divided by 1,000 kilograms is 10 meters per second squared. To the left. That's a large acceleration. Well, it turns out to be true. If you were a cannoneer and you're in charge of lighting the cannon, you had better stay out of the way, because cannons did blast backwards, both on the battlefield and on sailing ships. When you fired the cannon would come flying back at you. It was very dangerous indeed. In fact, on my cartoon cannon, I've drawn this little support thing on the back of it, which when the cannon tries to accelerate to the left, it'll bore down into the ground and use the earth to prevent the cannon from running off and destroying a whole bunch of, my own soldiers, I suppose, in that case. So that's a very large acceleration, but if I calculate the acceleration of the cannonball, here labeled A sub B, according to the same Newton's second law, and the same force, 10,000 newtons, but now a much lower mass, that's 2,000 meters per second squared. And I deliberately arrange it in such a way that nothing's stopping that cannonball, because I want to hurl the cannonball off into the distance. 2,000 meters per second squared. Yeah, boom, that's what cannons do. Newton's third law describes these forces as action-reaction. When the cannon on the cannonball and the cannonball on the cannon, those forces are equal and opposite. But the changes in motion that I get are in proportion to the mass, which is why, under the action of the same force, the cannonball has a large acceleration and the cannon has a relatively smaller acceleration.
Mm-hmm.